So good evening once again. I gave a talk a little while ago about thinking about buying a telescope for doing astronomy. This talk is the other end of that, looking at how you can take pictures of the night sky. And I'll say along the way, given this subtitle, how you can photograph the night sky without ridiculously expensive equipment. I'll say something about the fact that, yes, you can, if you wish, buy ridiculously expensive equipment, very expensive telescopes, but I'll show you that it's not necessary to obtain very nice images of the night sky. So what do you need? Well, you can start simple. You can just use a camera that would normally be used for taking daylight images. You can just use a camera and a tripod. You can, if you wish, invest money on telescopes and mounts. And alternatively, you don't have to buy a telescope. You could just say to yourself, okay, I want to use a camera and a so-called tracker. This is something I mentioned when I was talking about buying telescopes. You don't need a telescope. You just need to somehow take into account the fact that the Earth is rotating once a day, and hence the sky appears to rotate once a day. As long as you can somehow compensate for that and follow the stars, then you can take long exposures and get very nice images. So I'll show you how you can do that and tell you more about star trackers. I'll be showing you some of my images to convince you that it is possible to take nice images without a telescope, and then I'll finish with an experience of taking images under the darkest skies possible, i.e. in the middle of Africa. So let's start simple, just a camera and a tripod. If you wish, you can just take a camera, stick it on a tripod, point it at the sky, and expose, and you get images like this. Star trails, because the Earth is rotating. The North Star hardly appears to move at all, but all the other stars appear to wheel around it because of the rotation of the Earth. This was a few minutes exposure, so the stars haven't moved much, but I'm sure you can see that they have moved and trailed. If you take a longer exposure, the stars will move even more. So for instance, if you were to take a 6-hour exposure, each of the star trails has moved approximately 1/4 of the way round, because 6 hours is 1/4 of the rotation of the Earth, the 24-hour rotation of the Earth. Notice, I'll usually give details at the bottom here, this is not a single 6-hour exposure. With digital photography, it's possible to take a series of short exposures. Here I've taken a whole series of 1-minute exposures. I just effectively left the camera running and told it to take a picture every minute, and then I went away and did something else, came back later, and I had 6 hours of data. And software will add all of that up for you to produce star trails. Alternatively, you can use free software to add those all together and make a movie of the Earth rotating. In other words, a movie of the stars trailing in the sky as the Earth rotates. So if we can bother waiting for it, it would again produce 1/4 of a rotation. So that's what you can do with a camera on a tripod. Free software will allow you to take star trails or star movies if you want to see the stars rotating. It looks a little bit like daylight here because we've got a blue sky and we have these observatory buildings that look like they're sunlit. In fact, they're just moonlit. There was a full moon that night, and the full moon is shining on these white observatories, and it's making the sky a little bit blue rather than black. Some astrophotography, you just have to be in the right place at the right time. If you ever want to photograph a total eclipse of the sun, you have no choice but to go to the right point on Earth at the right time to get to the right place so that the disk of the moon just covers the disk of the sun. So it's not cheap in the sense that you have to pay to go somewhere in the world in order to see a total eclipse of the sun. But again, you don't need any fancy equipment. This is just a camera and a telephoto lens on a tripod pointed at the total eclipse. The corona here, the atmosphere of the sun, that sends lots of charged particles out all the time, and some of those charged particles, especially when the sun is very active, some of those charged particles hit the Earth and produce aurora. Again, right place, right time. If you go to the Arctic Circle or the Antarctic Circle, then sometimes you find that the charged particles from the sun, it doesn't really matter what they are, they're actually protons and electrons, but the charged particles from the sun hit the Earth's atmosphere and make the atoms in the Earth's atmosphere glow, these characteristic green and sometimes red colors. So you get these beautiful curtains of light when you have an auroral display. And these, I went to Iceland with some friends quite a few years ago now and took these exposures. Occasionally, the sun is active enough that aurora can be seen from further south, and some of you might have caught the aurora when they were visible a few weeks and a few months ago. You don't tend to get the same structures as we saw just a moment ago. You don't see the curtains of light, you don't see the arcs, you don't see the structures, but you do get some of the colors. And this, you notice, wasn't taken by anything particularly fancy. Just before I went to bed, I took out my phone, rested it on the windowsill, and took an exposure, in this case 3 seconds, and that was enough to pull out some of the color, very little of the structure because there wasn't much to see, but it was possible to capture some of the colors of the aurora. So the sun is very active at the moment, and for the next year or two it will continue to be active, and we'll almost certainly be getting more aurora as time goes by, so watch out for them. Also, you may know that we had a visitor fairly recently. We had a comet come through the solar system. It went past the sun, and for a while it was visible in the evening sky after sunset. So there you can see the comet and its tail. The sun had set when I took this picture, so the sun was way down here in the bottom right, and notice that the comet's tail is pointing away from the sun. Even though the comet is actually heading in that direction, comets don't fly through the sky trailing a tail behind them. The tail always points away from the sun. So it's effectively what you would expect as it comes into the sun, but as it leaves the sun, it actually flies off tail first, as it were. So this comet was actually heading off in that direction. It was only visible for a few nights, maybe a week or so. As it started to get higher in the sky, into a darker sky, unfortunately, because it's further from the sun, the tail gets a bit dimmer. The tail is the result of ice from the nucleus of the comet evaporating because of its proximity to the sun. So as it moves away from the sun, the tail gets less spectacular. So if you did want to move beyond, get a camera, stick it on a tripod, click, get something in the night sky, you can think about buying telescopes and mounts. So what would be the best telescope to buy for astrophotography? Well, you could argue the best telescope is that one. The Hubble Space Telescope was launched in 1990. It's now 30-something, 34, 35 years old, and it will be decommissioned in a few years' time. So watch out on eBay, because ultimately, I'm not sure if it's a buyer-collects sort of situation, but basically NASA will give up on it in a few years' time. It's still producing wonderful images. And if you've got $1 billion to spare, you can buy yourself something like the Hubble Space Telescope and get superb images of galaxies at great distances and nebulae such as the famous Pillars of Creation in the Eagle Nebula, which is visible from our skies. But if you did decide to buy yourself a telescope, you have lots of choice. As I said in the previous talk, you can buy telescopes that focus the light through lenses and telescopes that focus the light through mirrors. I've already been through the pros and cons, and I might have 1 or 2 leaflets if anybody missed that talk earlier today. But there's an awful lot of choice in terms of if an amateur was interested in buying a telescope, there's an awful lot of options out there. And if you did decide to buy yourself a telescope, then even looking at our closest neighbor, this is nothing to do with galaxies millions of light years away, just looking at our immediate neighbor can still be very rewarding. Looking at how the shadows of the craters and the mountains change from night to night as the moon goes around the Earth, and hence the angle of sunlight changes. So I was lucky enough to use a rather nice amateur telescope, amateur but still quite expensive. You could argue ridiculously expensive, depending on the depth of your pockets, but being able to see detail on the moon, and I figured that this projector wouldn't necessarily show you all the detail, so I've simply taken half of it and blown it up a little bit bigger. This is the sort of detail you can see through a nice telescope if your skies are nice and steady. Ideally, get away from street lights, but with the moon being so bright, you don't have to worry so much about light pollution because it's not a faint object. But you can see enormous amounts of detail in mountain ranges and craters, and if we look at the bottom half of this image, that's the crater Copernicus, made a long time ago and producing this sort of ejecta blanket. But again, you can spend many a happy hour at the eyepiece of a telescope just watching these features as if you were flying over the surface of the moon. And being so bright, it's relatively easy to take pictures of the moon. But astrophotography is not just about taking pictures of our nearest neighbor, it's about more remote objects. So if you did want to do astrophotography through a telescope, great, you can do that. But you need time, effort, and cash, because you need a reasonable telescope. That telescope must accurately point at the sky as the Earth rotates and follow the object if you want to expose not just for a few seconds, but for a few minutes or possibly even a few hours. You've got to make sure that the mount on which your telescope is placed can accurately track the sky as the Earth rotates. So that's a picture I took a few months back with the Pillars of Creation. Okay, it's not as good as Hubble's image, but yeah, you still get a certain amount of satisfaction taking pictures for yourself. That's a picture of a star that has sloughed off its outer atmosphere many thousands of years ago. This is what our sun will look like in due course. In a few billion years' time, when our sun runs out of its nuclear fuel, when it runs out of hydrogen, it's no longer going to be able to hang on to the outer part of its atmosphere, and the outer part of the atmosphere will end up producing something very similar to this, a so-called planetary nebula. Nothing to do with planets, it's just the name given to this particular structure of gas that's surrounding a star that's come to the end of its life. That's the remainder of the star, that's the core of the star that's left after the outer part of the star has disappeared into the interstellar medium. So this is what we think our sun will look like in a few billion years' time. And this is a rather nice picture of a nebula called the Trifid Nebula because of the sort of threefold petals in this particular part of the nebula. A glowing gas cloud of hydrogen and other elements. One of the reasons I'm showing these pictures, apart from showing off, is the fact that they actually are color. And it's a reminder that when you look up at the night sky, you see what? White stars on a darkish background. And you think maybe there's no color out there. The moon is grey. The stars are white on a dark background. But it's only when you take pictures that you realize the universe is actually colorful. Our eyes are not very good at seeing color when the light levels drop. But cameras are, a bit like those aurora pictures I showed before. When you see the aurora in the sky, you can hardly see any color. Take a picture, the colors come out, because cameras are very good at collecting light and adding up all of the photons of light that are arriving. Our eyes are not so good at that. Our eyes are really adapted to see in daytime. They're not really well adapted to see at night. So although getting a telescope and taking pictures is wonderful, you can get fantastic images with a telescope, it's expensive. And by expensive, I mean you can't really do it for a few £100s. It really does need, if you want to do it properly and get the sort of images that you see in magazines or on web pages, you pretty much have to spend thousands, not just a few £100s. But there are cheaper ways of doing astrophotography, and I'm talking about cheaper ways of doing astrophotography without ridiculously expensive equipment. And it means using a camera that you possibly have already got. One of my hobbies is wildlife photography. So I've got a camera anyway that I use for taking pictures of lions or zebra if I go on safari. That same camera can also be used for astrophotography. It doesn't have to be a special camera. It doesn't have to be modified or adapted to take pictures in the dark, i.e. at night. So I built myself a tracker because ultimately if you want to take exposures of more than a second or two, you've got to take into account the Earth's rotation. So I built myself out of bits of aluminium and a couple of AA batteries and a potentiometer and a little motor and a few resistors. I built myself a tracker. In other words, there's a couple of hinges at the back, and as this motor turns, it lifts this arm and it rotates the camera at the rate of 1 revolution per day. So as long as it's lined up right, as the Earth rotates, this tracker rotates the camera in the opposite direction, which means the camera hopefully stays pointing at the star or planet or object that I'm interested in. So you can build yourself a tracker. It cost me a few tens of pounds, and I've got instructions for how to build one if you fancy having a crack yourself. This I used for quite a few years, and eventually I decided to have a crack at one that was made for me. In other words, there are commercial suppliers. This particular one is made by a firm called Ioptron. There are at least half a dozen other manufacturers who make star trackers, some big, some small. And again, I can give you a guide to prices if you're interested. But the bottom line is trackers do not have to be as expensive as telescopes and quality mounts. You can get away with building one for yourself out of scrap almost. Alternatively, you can get a clockwork mount for maybe about £100 or so. A tracker is basically just a motor in a box. It sounds expensive for a motor in a box. It's a little motor and a gearbox and a worm gear that moves this round at approximately 1 revolution a day. The Earth doesn't actually do 1 revolution in 24 hours. It actually does 1 revolution in 23 hours, 56 minutes. And these trackers are designed to give you 1 revolution in 23 hours and 56 minutes. In other words, they are accurate precision devices. So we've got a bit of electronics to make sure that this motor turns at just the right speed so that the worm wheel makes this turn at the relevant speed to compensate for the rotation of the Earth. So basically, all trackers don't look like this necessarily, but this is the one that I'm showing you just because that's the one I used. It's a box. The camera mounts on this just like it would mount on a tripod, 3/8 or 1/4 inch Whitworth thread. And you can see the camera quite often is mounted onto something like a ball and socket joint, so that even though the tracker is set up to accurately be parallel with the Earth's axis, the camera can point wherever you like. You're not restricted as to which bit of sky you photograph when you're using a tracker. This device on the left-hand side is a tiny little telescope, which allows you to look along the axis of rotation and make sure that you're pointing at the pole star. In other words, make sure that your tracker is lined up in the same direction as the Earth's axis. So as the Earth turns that way, the tracker turns the opposite way, and you get nice static images of the sky without the stars trailing. So let me show you what you can do with the tracker. Some of these were taken with the tracker I built, some of these were taken with the tracker I bought. But basically, any tracker will allow you to get images like this, repeat, without using a telescope. So that's just a very quick selection just to show you that there are lots of different objects that you can photograph. Some of them are taken with a wide-angle lens, some of them are taken with a telephoto lens, but they're all taken with that camera. I just happen to be a Nikon owner. If you've got a Canon or a Sony or an Olympus or Lumix or any of these other cameras, they all produce wonderful images. And a reminder that the colors are real. None of this is false color. When you look at pictures from the Hubble Space Telescope, they've been colored in a particular way to bring out detail in the images. The pillars of creation aren't actually green and yellow. The pillars of creation are actually red, but Hubble images have been colored to try and bring out the detail. These are as nature intended. These are color pictures taken with a color camera, and I've tried to make sure that the color rendition of the final images is as close as possible to the actual color of these objects. So that is genuinely pink because it's made of hydrogen, and hydrogen glows pink when it's excited. And there's pink and blue because scattered light tends to be blue, whereas light from hydrogen tends to be more pinkish color. There's a red giant in there lighting up part of that nebula yellow. There's also a blue star in there lighting that up blue. Galaxies tend to be, well, sort of all colors mixed together, which is why they don't seem to have any particular color. This one on the top right is actually made of hydrogen, which is glowing pink, and oxygen, which is glowing blue. So these colors are real and meaningful. When you take a picture of these objects, you can actually deduce something about the object that you're imaging. So yes, astrophotography, if you wish, you can buy a telescope and a very expensive camera and a very expensive mount, and you can take absolutely superb images. And amateurs have indeed, for the last 10 or 20 years, been producing fantastic images from their back gardens. But beware, it will take time. If you buy equipment, if you throw money at the problem, it'll still take you a little bit of time to figure out what you need to do. It'll take time, it'll take a certain amount of effort, and most importantly, it will take a shed load of cash. If you want to spend thousands of pounds on that, go for it. You'll get fantastic images after a little while, not in the first 5 minutes. But you don't need a telescope if you want to do astrophotography. One thing to bear in mind is if you take images from a light-polluted area like the suburbs of Liverpool or the suburbs of Birmingham, you take a picture, you look at the back of the camera of the image you've just taken, and you think, that's horrible, it's just orange. That's because of light pollution. So there is actually a nebula in there that you can hardly see because there's so much light pollution. The street lights are lighting up the sky and you can hardly see the object of interest. But the saving grace is that software allows you to mitigate that to some extent. You can use software, some of it's free, some of it you might choose to buy, depends on your personal preference. Software will allow you to take images like that and process it in such a way that the background sky becomes rather darker and the object of interest, which is in there somewhere, now becomes a lot easier to see. The software allows you to take into account light pollution, and it allows you to, where necessary, increase the contrast, perhaps increase the brightness of the object to make it easier to see what you're imaging. Even better, get away from light pollution in the first place. Get away from the street lights. Go somewhere where you haven't got thousands of street lights around you. But if you are limited to taking images from a light polluted area, all is not lost. You can still get nice images even though you start off with some light pollution. So here's a few images. This was taken from a reasonably rural area, not too many street lights around, but this is a hydrogen cloud. It's a cloud of hydrogen which is condensing and stars are being born in the center. So this is a stellar nursery, if you like. This is a few thousand light years away, and it's been doing this for quite a while. Of course, most astronomical images are effectively snapshots. We haven't got the patience to watch this for 500,000 years to see what happens, but we think these stars are relatively recently being born, and they've been born out of the hydrogen cloud, which is slowly collapsing over time. We came to that conclusion by watching lots of these hydrogen nebulae collapsing and seeing the stars that are being born at the center. This is a star at the end of its life rather than the star at the beginning of its life. This is a nebula called Eta Carina. There's a star embedded in the very brightest part of this nebula. This star is really massive and really unstable. And for thousands of years, this star has been shrugging off some of its outer layers. That's why we think this is a prime candidate for a star that's going to go supernova before too long. Before too long could be tomorrow, could be 1,000 years, it could be 10,000 years. That's tomorrow as far as astronomical time is concerned. But we are fairly sure that this is a massive star coming towards the end of its life because it seems to be so unstable. And pretty much everything you can see here in terms of the nebulosity was once part of the star and has now been released after thousands of years into, again, the interstellar medium. And somewhere right at the heart is a star that's going to go supernova before too long. One thing to notice is that we're not talking about photographing objects with ridiculously long telephoto lenses. This is an 85mm lens. The focal length, it's the sort of focal length that you probably get in a very short zoom lens that comes with the camera that you've bought, if you've bought a digital SLR or a bridge camera or a mirrorless camera. So we are not talking about long focal lengths to see really small objects. This is large enough in the sky that we only need a very modest focal length in order to get a nice image like that. This particular object is one star that has gone supernova in the past. We don't know which star it was. It's probably not visible in the middle there, but this effectively is a bubble of hydrogen and oxygen from a star that went supernova thousands of years ago, and we're now seeing the shock waves as this supernova shock wave expands into the interstellar medium. And again, in this particular case, I've taken a telephoto lens, and this is one of the few cases where I've actually used a filter to image this particular nebulae. Some objects, again, have beautiful color. There's a blue star lighting up this part of a cloud. There is a red giant over on the left-hand side lighting up this region in yellow. So you get beautiful colors coming through with, again, to re-emphasize, Hubble images will be false color. This is the actual color of the sky as imaged by the Nikon camera and a 300mm lens. If you wish, you can look further afield rather than looking at objects within our galaxy. There's our neighboring galaxy, the Andromeda galaxy. Again, a modest telephoto lens, the sort of telephoto lens that I would use for wildlife photography. The lens is about 150 or so millimeters in length, relatively lightweight, easy to carry around. easy to put onto a little star tracker. Again, not one long exposure, but a whole series of 1-minute exposures all added together, and then you can see a huge amount of detail in the Andromeda galaxy. You're not limited to taking our own neighbor, Andromeda. You can look further afield. Here's a whole load of galaxies that are strung out into a sort of string. They're all gravitationally tugging on each other. So these galaxies were probably born at the same time, and they seem to be on this sort of string, and probably these are related to the same cluster as well. It's a cluster called Markarian's chain. It's about 50 million light years away, this particular chain. So the light that left these galaxies to produce this image left these galaxies when there were still dinosaurs roaming on the Earth. And it's taken 50 million years for the light to get from there to the camera. But that's by no means the limit of what you can do with a camera. Even a camera that's designed to work in daylight, you can still go further afield again. During lockdown, when I couldn't go to the pub with my mates, I decided to see what is the most distant thing I can possibly catch with my camera. And so I used my tracker, put a Nikon and a telephoto lens on the tracker, and then looked by looking up in a catalogue, what's the most distant object am I likely to be able to see? It turns out there's a galaxy, this is just a bright star, there's a galaxy top right of that star, which is very, very, very distant. So I asked myself, is it possible to catch that with my camera? So I went out in July. There's not much of a night time in July, of course. I took exposures for as long as I could. I took a whole series of 30-second exposures, added them all together, and then looked in that square to see if I saw this very, very, very distant galaxy. And it's not very impressive, but that's it right in the middle there. The least impressive picture that I've got in this particular set. But when you consider that this particular galaxy, it's called a quasar. A quasar is just a galaxy with a very active nucleus. The nucleus of this galaxy is producing a lot of radiation so that I can see it even though it's at a huge distance away. If I blow it up, basically it's only 1 pixel or thereabouts, maybe a few other pixels. I made it a bit brighter to see. So it's a 20 megapixel camera, but most of the light from this distant galaxy has only gone into 1 pixel. But when you think about how far away this object is, it is absolutely mind-boggling. It's not millions of light years away, so that the light has traveled for millions of years. It is 25 billion light years away. The light has been traveling to us for over 12 billion years. The light from this galaxy left the galaxy even before the Earth existed. Even before the sun existed, light from this galaxy was on its way to us. And the universe is expanding. We know that from lots of evidence over the last century. The universe is expanding, and so these distant galaxies are actually getting carried away from us. And at the moment, the recession speed, the speed at which this galaxy is receding from us, is approximately twice the speed of light, which is, again, absolutely mind-blowing that even though a galaxy is receding from us faster than the speed of light, it is still possible to catch the light from these ridiculously distant objects. And it's possible to do it with a camera that was designed to work in daylight. So if you're interested in astrophotography, don't assume that you need to buy astronomically relevant equipment. You can just use the camera you've already got. So let me just finish with how I like to spend my holidays. It's nice to get away from streetlights. I'm interested in wildlife. I'm interested in photography, and of course, taking pictures of animals is interesting. It's also possible to do astrophotography because astronomy and photography go together if you want to take pictures of the night sky. But if you're going somewhere interesting, like on safari in Africa or to a remote place away from streetlights, then wildlife and astronomy sometimes go together, because if you're going somewhere remote enough to see interesting animals, it might also be far enough away from streetlights that you can do some astronomy as well, possibly with the same binoculars or possibly with the same camera. So for my interest, these three overlap on safari. Basically, take pictures of animals by day, take pictures of the stars at night, sleep when you get home. I mean, there's no point in wasting time on holiday, is there? So if you look at the Milky Way as seen from the UK, you look up, if you get away from streetlights, you can hopefully see the cloudy stripe of the Milky Way across the sky. But it's only when you get away from streetlights that you realize just how bright the Milky Way actually is. Our own galaxy, by the naked eye, you can see all of this structure if you get away from streetlights. If you get away and go to a nice dark sky, there are a few parts of the UK that fit that description. There are certainly parts in other continents that fit that description. You look up into the sky and you see an enormous number of stars, and you see all of this structure in the Milky Way. You don't see color because your eyes don't work in color at night. But if you take a picture of the Milky Way, then the picture you take will bring out the colors. In this particular case, as well as having dozens of star clusters and nebulae and all sorts of other interesting things going on, there's also two interlopers in this particular image. That's the planet Jupiter and that's the planet Saturn, which happened to be in the field of view when I took these images of the Milky Way. So I guess the take-home message is, if you're going anywhere interesting in the world, or you're getting away from streetlights in the UK for whatever reason, think about a star tracker, build one yourself, or buy one at a relatively modest cost, and then you too can take images of the universe. Thank you very much for listening.